I'm Adam from RFOXiA from our real lab. Today we are answering why does firmware flashing fail and why the programmer is almost never the reason. There is a particular kind of frustration that comes from debugging the wrong thing. You have a failed firmware upload, the IDE says it failed, the STLink says it failed, so you replace the cable, same result. You reinstall the driver, same result. You swap the STLink for a different unit, same result. At some point, you conclude the chip is defective and you move on, and you have learned nothing because the chip was not defective and neither was the ST-Link. The problem was the power supply. It was the problem the entire time. Let me explain what is actually happening during a firmware flash operation, because this is not complicated physics, it is just physics that nobody bothers to explain. When your ST-Link initiates a flash write cycle, the target microcontroller does not sit there passively, it wakes up. It engages its internal flash programming circuitry. It charges internal pump capacitors to generate the elevated voltages required for program and erase operations. It draws a current spike. On a well-designed bench supply with adequate output capacitance, that spike is absorbed and the supply voltage holds steady. On a USB port, which is what most people use to power their targets during development, that spike causes a voltage sag. Sometimes a few millivolts, sometimes a few hundred millivolts, sometimes enough to cross the brownout detection threshold. If the MCU brownouts mid-write cycle, one of three things happens. The write operation is aborted cleanly if the hardware caught it in time. The flash page is left in a partially written state, which usually means corrupted firmware that will not boot. Or the MCU resets, the programmer loses connection, and you get an error that looks to every diagnostic tool in your environment exactly like a programmer fault, because the programmer dropped its connection. It did drop its connection, but it dropped its connection because the target microcontroller reset under it. The ST-Link did not cause the reset. The power supply caused the reset. The ST-Link just noticed it. Now add ground noise, because this is also real and also underestimated. USB ground is not a quiet reference. Every device on that hub is switching. USB controllers are switching. Motor drivers, if you have any in the system, are definitely switching. Every switching event injects noise onto the ground plane. If the ground reference of your target is not the same stable ground reference that your programmer is measuring voltage against, the SWD signaling can degrade. You get bit errors in the data stream. Those bit errors look like communication failures. They get logged as programmer errors. They are not programmer errors. There is also a subtler version of this problem, which is current starvation without a full brownout. The supply voltage never quite drops below the reset threshold, so no reset occurs. But the MCU is running slightly starved during the flash operation, which means its internal timing references are slightly off. Internal oscillators drift. When supply voltage drifts, the flash controller's timing margins tighten. Some write cycles complete correctly, some do not. You get an image that partially flashes, boots, and then exhibits strange behavior that has no apparent cause in the firmware itself, because the cause is not in the firmware. It is in corrupted flash cells that wrote incorrectly and are now holding wrong values. This is the failure mode that costs the most time because it is inconsistent. It does not always happen. It happens when the USB port is under load. It happens when a motor is spinning somewhere nearby. It happens on cold mornings when your bench capacitors have higher ESR. Inconsistent failures under inconsistent power conditions. The diagnosis points everywhere except at the power supply, because power supply problems are invisible without a scope on the rail during the flash operation. Here is what clean power actually requires for reliable firmware programming. The supply voltage must remain stable within the MCU's specified operating range throughout the entire flash cycle, including peak current demand. The ground reference must be shared solid and low impedance between programmer and target. The current delivery capacity must exceed the peak demand of the flash programming circuitry with margin, and if you are powering the target from the same source as the rest of your development environment, that source needs adequate bulk capacitance to absorb transients. A supercapacitor-based power system satisfies all of these requirements simultaneously. A supercapacitor is, in electrical terms, an extremely large capacitor. Its job is to supply current instantaneously when the load demands it, without the voltage sagging because the energy is stored locally in a form that can be discharged without delay. When the MCU's flash circuitry draws its peak current during a program or erase cycle, the supercapacitor delivers that current without the supply rail moving. No sag, no brownout, no reset, no partial write. The flash operation completes, the programmer reports success, and the firmware is exactly what you uploaded. When the programmer and the power supply are part of the same design system, the ground reference problem is also solved. There is no USB hub between them. There is no separate wall adapter with its own ground. There is one common reference, and both devices speak to the target from that same reference. SWD signaling margins are what the silicon specifies, not degraded by ground offset. The reason this matters for RFOXiA modules specifically is that the BLE module is doing sensitive RF work. Its supply rejection requirements are tighter than a generic MCU. Noise on the power rail during operation is noise on the RF path. A module programmed with marginal power, even if the flash operation technically completes, may exhibit behavior during RF. That is the physics: voltage sag, ground noise, and current starvation. Three problems that the STLink gets blamed for and did not cause. Now let me show you the hardware that solves all three. This is the supercapacitor bank at the core of the power program kit. 1100 farads of storage, 8800 joules of energy. When your BLE module's flash controller draws its peak current during a write cycle, this bank delivers it without the supply rail moving by a single millivolt. No voltage sag, no brownout, no mid-flash reset. The firmware lands where you put it, intact, every time. It charges fully in under 5 minutes. The 12-volt 5-amp charging adapter is what refills the supercapacitor bank at the rate it needs, charging at 4 volts 10 amps into the bank directly. This is not a trickle charger, it is matched to the bank's intake capacity, so you are not waiting. 5 minutes and the system is fully charged and ready for a full day of development. The adapter ensures the bank is always at capacity before your session starts. The entire Multinav Pro Plus module stack, BLE module, GNSS module, sensors module, can run from this single power source for a full working day. That matters in the field where your programming environment and your sensor deployment are the same device, and a dead battery means a wasted trip. One charge in the morning, one full day of operation. The bank does not fade the way a lithium cell does. It holds voltage flat until it is depleted. The STLink programmer in this kit is not a generic unit dropped into a box. It is integrated into the power and ground architecture of the kit, which means the programmer and the target share the same reference. No USB hub, no separate supply, no floating ground. SWD signaling operates at the margins the silicon specifies, not the margins your development environment happens to provide. Firmware updates and debugging sessions run without the ambiguity of shared hub ground offsets. Every cable in this kit is the cable the system was designed for. The flat ribbon cables connect the BLE module to the power module and the programmer to the BLE module with defined impedance and defined geometry. There is no substitution, no adapter chain, no question about which cable is correct. You plug in what is in the box and the system operates as a designed unit. That is the point, not individual components, but a matched environment where every variable that causes a flash failure has been removed. Data in flash, configuration that was written incorrectly because the right conditions were marginal. You will spend days wondering why your link budget does not match spec before you discover that a register was written wrong because your USB port sagged 40 millivolts during the erase cycle. The power program kit pairs your STLink with a clean matched power environment so firmware uploads complete reliably the first time, every time. That sentence is not a marketing claim, it is a description of what clean power and a shared ground reference do to the physics of flash programming.